Okay, so for today we're going to be looking at a really short lesson, thinking about the math in a completely different way. Where did the speed of light come from? So EMR travels at the speed of light. We discussed this yesterday, and that it's uniform if it's in the same medium. But how do you measure something that's traveling at 10 to the 8th meters per second? Galileo tried many years ago. He stood on a hilltop, he flashed a lantern, and then his assistant, as soon as he saw it, flashed the lantern back. And Galileo knew that he knew the distance between the two hills, that he could figure out the time. The theory is great, but Galileo was way off in what he understood it to be. Then along came Ole Romer, and he measured the speed of light using the eclipse of Jupiter's moon. So he knows that in one season of the year that Earth and Jupiter is close, and at the other season of the year Earth and Jupiter were far apart. And because he had a kind of an idea of the distance of the planets based on other people's work, he made a rough calculation on the speed of light. Today, standards, he is way far off. He was way far off the 3.0 times 10 to the 8th, but it was the first attempt at figuring it out with any kind of solid knowledge of what's going on. Along came Fizeau, and what he did was he used a cog wheel with notches in it, and he spun it, and he shone a light, and he figured that if he had the timing just right, every time that the cog spun, if it was the cog side out, it would block the light and the observer would not see the light, or if the cog turned perfectly in the right period, that the observer would always see a continuous beam of light. And so he was working on this concept of period and rotation and observation of light. The way that he had it set up, the light source, shining through the cog off of a mirror and back and reflecting up to an observer looking through a telescope, because he was about 8.5 kilometers away from the first mirror that it was hitting. Then he was able to actually calculate out the speed that the light was traveling at. He was actually probably one of the most accurate for the day. He had only about a 5% error of the actual speed of light, doing it this particular way. But what we work with and what we observe is Michelson, and we do quite a bit of this. You'll see a Michelson question guaranteed on the diploma. He used a spinning mirror apparatus instead of a spinning gear. And so the reason his method worked really well is he used an 8-sided mirror. So he had something that wasn't so divided up like the cog, but still had consistent divisions. And so the beam of light hit one side of the mirror and reflected on a stationary mirror. The beam bounced back to the rotating mirror, and as long as it was spinning at exactly 1/8 of a turn, or 1/8 of a period, the next side is in the correct position to reflect the light exactly back to an observer looking through a telescope. So the period, the sides would have rotated 8 turns to make a complete period. Okay, this is really important to try and figure out in your mind. So the first question that we're going to look at is when Michelson did his experiment with the curved mirror 35 kilometers away, he found that the 8-sided mirror needed to spin at 32,000 RPM. Using this information, we're going to figure out the speed of light based on Michelson's experiment. So what we see here for information, red pen, is distance is 35 kilometers and frequency is 32,000 RPM. Now RPM stands for revolutions per minute, and the definition of a frequency is cycles per second. So we need to take this and convert it, revolutions per minute, and convert it to seconds. So in 1 minute, there's 60 seconds for a total of 533.3 hertz. This distance is in kilometers, which is not a unit that we work in. We work in meters. There's 1,000 meters in 1 kilometer. Okay? Amy discovered this yesterday, when you enter in, if you do it this way, 35 times 10 to the 3, don't go 35x 10 to the power of 3. Your calculator doesn't like that. Go 35 EE3. I don't know why, but this is how the calculator works. Okay, so it's asking us to determine the speed of light. We're working in air, so we know that we can use this formula. Okay, but we don't have time. How do we figure out time? Period is going to be equal to 1/8. Time is going to be equal to 1/8 of the period. We don't have period though. Period comes from knowing the frequency. Okay? So let's start with the information that we know. So your period is going to be 0.001875 seconds. But now we need to find the time. The time, it was 1/8. If the mirror turned 1/8 of a turn, then it would work. So 1/8 of the period. And we see that this comes to, this is 23437. You're going to keep all of your significant digits. It's still seconds, even though we're a little t now and period is also in a second. It's all time. And then we can figure out our velocity. Lo and behold, Michelson actually got fairly accurate results. Let's look at the next example. Using an experimental setup similar to Michelson, using a 6-sided mirror, students found the speed of light to be 2.95 times 10 to the 8th meters per second. Kudos to the students. The mirrors were placed 45 kilometers from the fixed mirror. What was the frequency of the rotation of the mirror? What information do we have? Velocity equals 2.95 times 10 to the 8th meters per second. What's the distance? 45 kilometers. Taking that to meters. Okay? And it's asking us for the frequency. How do we find frequency? Frequency is equal to 1 over t, if you just rearrange that formula. Period can be found by 6 times the time it takes for the whole thing to rotate. So each side is considered 1/6 of the period, so you have to multiply it by 6. And then from here, we still don't have time. Velocity equals distance over time, or time is equal to distance over velocity. Okay, so let's start. time is going to be equal to 45 times 10 to the 3 meters divided by 2.95 times 10 to the 8th to give us a lovely value of 3.0508, and you're going to keep the rest of the decimals, times 10 to the negative 4 seconds. Now we're going to look for the period. 6 times 3.0508 negative 4 is going to give us units don't change, we're still in period. But from there, now we can figure out frequency. Frequency equals (546 hertz). Okay, so we've figured out frequency. So now what we're going to do is we're going to work on the questions at the bottom here. There are a lot of questions, so I'm not going to double up this lesson. And you also need to work through the practice problems. Be prepared tomorrow to write entry ticket.